Good afternoon, grade 8. Welcome to this first lesson of the third term. So far, we have dealt with term 1 and 2 work. From this week, we are starting on term 3 work. And I hope that you will be with me, talk to me, so that you understand the concepts and skills we are trying to teach you here. It's very difficult to teach skills in this fashion. I hope that we will cooperate so that whatever skills we share here, you understand and you can practice in every way that you can, if it's possible. We are starting with mechanical systems and control. Some of the work that we'll be looking at today is what you did in grade 7 under mechanical systems and control. So a bigger part of this lesson today will be revision of grade 7 work, and then gradually we'll be moving into grade 8. This is what you'll be doing. Revision of levers, classes of levers, examples of first-class levers, examples of second-class levers, examples of third-class levers, and then we'll look at that from grade 7, and then we'll try to elevate the level to grade 8. Right. The importance of mechanisms. I think we have discussed this before, that we try in technology to use mechanisms to make our lives easier. Mechanisms are parts of machines that help us to move things. Machines are usually made of many connected mechanisms. Some parts of a mechanism move, and other parts are used to hold the moving parts in place. So, a mechanism is the basic part of a machine. It's what machines are made of. So, a combination of mechanisms is a system, and a machine is a combination of many systems. Okay, Natalie, we'll look into that. I also like Kahoot, but we'll look into that. We'll look into the school policy, because the school has its own policies. We'll see if we can do this. So let's talk about mechanisms. I'm explaining that mechanisms are the basic part of machines. So when you connect mechanisms, you make up a system. But a machine may be a combination of many systems. Or it can be, a machine can be a combination of one system if that's sufficient to make up a machine and it serves the purpose for which the machine is made. But other machines have different systems. Think of a car. A car is a big machine. It has many systems. It has mechanical systems, different mechanical systems. It has electrical systems. And those systems, they are combined together, they interact to make the car move, to make the car serve the purpose for which it was made as a vehicle. So mechanisms are the basic part of machines. I hope you understand the word mechanisms. Mechanisms are useful because they help us to move things further, faster, or by using less force. Just imagine if we didn't have cars. We would use other means of transport, those traditional means of transport, thanks to the people who invented the wheel and they invented engines. And here we are today. We can move things. We can do things easier by means of many other machines that we have in our technological world. Now let us look at this fellow here. He's trying to move this big block, and he's making means to move this block because obviously perhaps he cannot lift it up. So he has to use that stick so that it gives him some form of mechanical advantage to move this big block. But when you can look under the stick, you find that yellow stuff there. He made a pivot or a fulcrum for himself so that this fulcrum can make it easy for him to lift this load. And this is a mechanism. The big block, the fulcrum, and the stick, it's a mechanism. So he is using this mechanism to make his life easier to move this load. And if you can remember from your mechanical systems in grade 7, can you classify this lever? Try and remember, perhaps you can. Let's see if you can remember the classes of levers from grade 7. Very good, Lesedi. It's a picture of a first-class lever because you have, between your load and your effort, you have your fulcrum. So that is one big characteristic of first-class levers. Now the effort is the input force. It is the effort. And the output force is the one that is lifting up this load. So the load in this case is a block, a big block. So this is just a mechanism, all right? And on the principle of this mechanism, other machines can be built, all right? So I want to just help you remember these classes of lever that you did in grade 7. You have your typical first class lever, like the one that you just saw on the previous slide, which we said is one where the fulcrum is in the middle. And there's just this one popular example of a first class lever. I know you like it. I know when grade 8 and grade 7 start thinking of levers, this comes to mind. What other example do you know of a first class lever? The most common one that you liked as children. Grade 8. Another example of a first class lever. What does this lever look like? What does it look like? Doesn't it remind you of something? I'm trying to get to your chat. Right. Lesedi, yes. Yes, the seesaw. It does look like the seesaw, ne? Zamokushe. Yes, Helen. Yeah, it looks like a seesaw, the first class lever. Actually, the seesaw is an example of a first class lever. So this just reminds you of the first class, the seesaw, this illustration of the first class lever. You have your fulcrum in the middle. So you always remember that. That's the first class. Asanda, yeah, I was about to say Zwinki Zonko. Zwinki Zonko, yeah, the seesaw, that's what you call it in the township, Zwinki Zonko. But I hope you don't write that in your test, okay? The correct word is seesaw. Okay, so second class levers are characterized by the load, which is in the middle between the effort and the fulcrum. Third class levers, they have the effort between the fulcrum and the load. So grade 8, I hope this is what you did when you were learning for your tests in grade 7. When you want to remember your classes of levers, you must just remember FLE, flare, FLE. Now the F is class 1. It means, what do you find in the middle of your lever? You find the fulcrum. L, what do you find in the middle of second class levers? You find your load. E, same. You find effort in the middle. So that's how you remember your classes of levers. Even if maybe I can ask you, because I will ask you as we go on with these lessons, I can show you something and ask you, what class of lever is this? You have to remember how you characterize the classes of levers. Then you can apply your knowledge of classification of levers. So I hope that helped. Right. Now let us look at examples, because what we learn, we must apply. Examples of tools with levers. Okay. We will go on and add others in this lesson as we go. Right. First class levers. I said you must look at the relationship between effort, load, fulcrum. So the position of these two, they will tell you what class of levers this is. Now, as you can see, class 1, the examples that are given there is a hammer, a claw hammer. Now, in this regard, the claw hammer, because it's pulling with its claws there, it's pulling out a nail. So, being used like that, in that position, the claw hammer is a first class lever. Let us look at why we can say that. You have your load. The load is where the claws are pulling out the nail, and the fulcrum is where the hammer touches the ground for support. It's pivoting there, where it says F, that's the fulcrum. Then the effort is where the user of the hammer will be handling the hammer. So because we have this fulcrum between the load and the effort, that becomes a first class lever. Pliers, same, but I want to draw your attention to pliers. As you might have learned in grade 7. Pliers are a combination of two levers, okay? Because if you take the top part of the pliers and the bottom part, you can see that this is these are two levers combined at the fulcrum. Because you cannot use scissors, pliers, even scissors, yes, they are first class levers. And they are a combination of two levers. You cannot use one part only. You have to combine these two first class levers to make pliers or to make a pair of scissors. So it becomes a first class lever, right? Let's just look at the wheelbarrow. We are not told where's the pivot. We just know the pivot is at the wheel. This illustration doesn't show us where the pivot is, but we know the F. Oh, there's a little F there. The F is on the wheel. So that's our pivot. And between the pivot and effort, you have your load. The load of sand or whatever you're carrying with the wheelbarrow is between the fulcrum and the effort. So that's a characteristic of second class levers. You have your nutcracker also. The same goes for the nutcracker. You see, it works almost like the wheelbarrow because you can see the nut there as the load between the effort and the fulcrum, right? Now you have your third class levers. Let me draw attention to the human arm. I remember in one lesson I was teaching grade 7 about levers. I looked at this arm. I hope this arm doesn't appear in any assessment because like that, the arm looks like a first class lever because of the positioning of the effort and the load. As you all can see there, the fulcrum is between the effort and the load, but I got another good illustration of why we would say the arm is a third class lever. We'll go to it. Then you have your sugar tongs, the same. Let us use this, the sugar tongs. There's your load right at the end of the lever. And to use the tongs, you have to put your finger, which is the effort, there on the arrows there, where it says E, that's the effort. See? To use these tongs to lift the load, you have to put the effort there. So the fulcrum becomes the end, okay? So that's a typical third class lever. Okay, I hope you understand. Let me just clarify this arm thing. There's our arm. Right. Let's look at the relationship between load, effort, and fulcrum. Now, this is a good illustration, much better than the one in that slide. Now, where it says effect, that's our load. Okay, grade 8. Where it says effect, that's your load. Now, let's see. You have your fulcrum on your elbow. But, you know, guys, you can identify, after revising these classes, you can just check the joints of your body. See how those joints operate. Then you can decide which class of lever is that, because we do have levers in our bodies. Okay, you can even look around in your environment, in your home, see how your windows open, the pedal pin and other things. Try to identify classes of levers around the environment. But let's go back to this one. Now, then the hand is handling a hammer. Now he's hammering in that nail. So that will be the load. The effort is on the hand. Then the fulcrum is the elbow. Think of the nutcracker. This arrangement is very much like the one of the nutcracker. You have your fulcrum here, okay, and your effort in the middle, and your load. Okay, so this classifies the arm correctly as a third class lever. All right, I know this other one can be very confusing. This one, if I was in grade 8 and I was given this in an assessment and asked to classify it, I would just classify it as first class because of the arrangement. Okay. Now, I hope you understand this part. What is the effort? The effort is the input force. That is you must, because when we study systems, when we study mechanical systems, you want to see, because we even calculate mechanical advantage. So it's very important that we identify the effort in the system. So in levers, the effort offers resistance. Okay. So it is this resistance. In this case, you see a balance there. You see a balance between the effort and the resistance. The effort and the resistance will be balancing against the fulcrum. So it is the fulcrum which will offer the effort and the load some balance. So the effort is the input, the output is the resistance, all right? Okay. The output is on the load, okay? Now, let's look at our environment, okay? I don't know if you have this tool at home, but me too, I don't have it. But somebody might have it, but let's look at this bolt cutter. Remember, we said a pivot is the point at which the lever turns. The fulcrum is the point at which the lever turns. Now, we have to ask ourselves, can you identify the pivots on this bolt cutter? Right? It has many pivots. Let's see. It has 5 pivots. There's a turning point here, another turning point there, another one there, another one there, another one there. So it was found necessary to make this tool like this so that it will give good mechanical advantage to cut this, to cut strong chains. So it had to, it won't be like maybe like a pair of scissors. No. If it was or pliers, no. You can cut a piece of wire with pliers, but if you have to cut this very solid chain, you need a tool like this. So some levers, they have multiple pivots like this one, okay? Even the pair of scissors is a little bit complex because it's a combination of 2 levers, okay? So here you have 5 pivots as well. It's a little bit complex. So this just to clarify that it's not always that you will find application of a lever system in the standard way that I have shown you in the previous slides, that you just have pivot here, load, and effort there. Sometimes you find a combination of those, okay? Like in this bolt cutter, for you to apply your input force, you have to apply it on both ends, on both arms. You see? So the input force is on both sides. All right. So the application of these mechanisms can be complex. So we have to look at every machine that we come across and try and identify how many levers can you see there? How many pivots? You know, some items in your environment are a combination of different types of levers linked together. Okay. Now, we are continuing with levers at home. Levers allow you to change the direction of movement, the size of movement, and the amount of input force that is needed for the output movement to happen. Okay? If you were to pull that nail with your hands, you would take perhaps the whole day. So this mechanism of the claw hammer, this lever, it's a lever. And you said, what class of lever is it? What class of lever did you say this is? Grade 8? First class. Chedza Lesedi, very good. First class. Helen, very good. Yes. Lesedi, yeah. We are going to learn about single and linked class, all classes, you saw that we did all classes of levers, because back from grade 7, you were doing different classes of levers, my children. So this is like a revision, right? Okay. Now, in that slide, you saw a claw hammer being used to pull a nail from wood. The long handle of the hammer gives you big mechanical advantage. As I said, if you had to pull this with your hand, you would take the whole day. So you want something that will make your life easier. So that's the claw hammer. All right. So that you only have to apply a small force on the tip of the handle for the claw of the hammer to pull out the nail with a big force. Okay, if our systems have mechanical advantage, the input force that we apply has to be multiplied in the output. So we know this is a good machine. It's really making our lives easier. Also, the rounded shape of the claw means that the nail is pulled out smoothly. Okay, so this is a first-class lever, as you correctly said. Okay. Another example of levers at home. Levers allow you to change the direction of movement, the size of movement, the amount of input force that is needed to for the output movement to happen. A bottle opener. Okay, a bottle opener. You can look at the arrangement of this. Let's see. The effort is here. The fulcrum is here. And the load is here. The load is here. What class lever is this? Where the load is between the fulcrum and the effort. Grade 8. What class of lever is this? It's a second class lever because the load is between the fulcrum and the effort. Okay. This helps you to remove a steel bottle cap by bending the cap. The length of the bottle opener gives you mechanical advantage, which means you only have to apply a small force to bend the cap. Second class lever, very good. Molemo, Cheryl, Natalie, very good, my children. So the mechanical advantage lies in the arm, okay, the length of the bottle opener, okay. So that's your second class lever. Does it make your life easier? Yes, because otherwise you would be biting these caps. And you know, our parents always tell us not to do that because you'll break your teeth. Pair of scissors. We've been talking a lot about pair of scissors, and I've already told you that it's a combination of two levers. Pair of scissors, it helps you to cut paper. Cutting knife will also cut paper, but it will cut the table surface underneath the paper as well. With scissors, the surface underneath the paper is not damaged. In fact, you can hold the paper in the air while you cut. I'm just thinking of fabric. If I want to cut fabric, you cannot do that with a knife. So a pair of scissors are really good. Okay, they make our lives easier. They do give us mechanical advantage. Same as pair of pliers. Because of the long handles, it also gives us a mechanical advantage. Right, let us look at mechanical advantage. What is mechanical advantage? Surely you have done something on mechanical advantage already. You already know that the input force is smaller than the output force. If the input force is smaller than the output force, there is mechanical advantage. We don't want to work very hard for a small output. Okay? You can say that the mechanical advantage is bigger than 1. If the mechanical advantage is bigger than 1, then it does make our lives easier. It's worth the effort. But if we put effort and we do not get the desired output, then that system is not good enough. If the input force is bigger than the output force, then there's no mechanical advantage, but rather a distance advantage. You can say the mechanical advantage is smaller than 1. Okay? When engineers, scientists, and technologists design mechanisms, they want to know exactly how big the mechanical advantage in a system is. It is not good enough for them to say that the mechanical advantage is bigger than 1 or smaller than 1. They need a number to tell them exactly how big or small the mechanical advantage is. We call this number the mechanical advantage. That's why we have to calculate in our systems, we have to calculate the mechanical advantage. If we see that our system does have mechanical advantage, then we go further to determine what is the value of that mechanical advantage or the amount of that mechanical advantage. That's why we do calculations. Okay, we'll proceed to do calculations. We'll use formula and then you'll see how we determine the amount of mechanical advantage each mechanism can give us. You can use the abbreviation MA for mechanical advantage. The mechanical advantage is calculated by dividing the output force by the input force. Let me tell you, my children, maybe if you Google or maybe in your textbooks, if you look at the formula for mechanical advantage, generally for different kinds of systems, it will be load divided by effort. Okay, load divided by effort. Output force is load divided by input force. We just said input force is the effort. I hope you understand that. You can also say that the mechanical advantage is the ratio between the output force and the input force. Okay, I put in so many newtons of force as input. What do I get for the output? Okay. Let's see how we calculate mechanical advantage. Okay, if a lever makes it to lift a heavy weight, the input force is less than the output force. I've said this, okay? And the mechanical advantage is greater than 1. For example, if the output force is 12 and the input force is 4, the mechanical advantage is calculated in the following way. 12 divided by 4. It can also be written as a fraction, okay? 12 divided by 4. Okay, that is load divided by effort, because this output force is the load. The value of the load is 12 in this case. And the input, the effort, is 4. So this is correct. The calculation is correct. It's load divided by effort. The answer to this calculation can be written in different ways. A ratio of 3:1. Okay. 3, how many times does 4 go into 12? 3. So I get 3 as my output for an input of 1. So the answer for mechanical advantage can be a value of 3 or a ratio of 3:1. So when you're asked to do your mechanical advantage calculations, your answer, you must understand your answer. You don't just do a calculation, you understand the system, or you interpret. You must be able to talk about it in an interpreting fashion to say for an effort of 3, there is for an output of 3, there's an effort of 1. So this is good. For 1 effort, you get 3 outputs. So this is mechanical advantage. Okay? This means that the output force is 3 times greater than the input force. You can also say that the lever gives a mechanical advantage of 3. Okay, we said initially, if a machine has a mechanical advantage, it will be greater than 1, but that is not enough. We must look at the values and do calculations. So this is how you calculate. Okay, how do you calculate it? In every system, you look for the load and you divide it by the effort. In every system, this time we are only doing levers, but we can do any other mechanical systems. This will be the formula. Okay, let us look at a mechanical advantage of 3 for us to understand better. Okay, but you cannot get something for nothing. If the input is 3 times less than the output force, you will have to move the input arm 3 times further than the output arm. Okay, let's see. Right. There, where it says lever moves 3 centimeters here, that is where the effort is. Small effort force. Okay. When you move that, the lever moves 3 centimeters as an input, and the lever moves 1 centimeter as output. Load force is 3 times greater. Okay, but then the load force, we must differentiate between the force and the distance. Okay, the force and the distance. You see, the distance here is 3 centimeters and the distance here is 1 centimeters. So the input distance is greater than the output distance, but there is a small effort, a small input force, but you get a great output force. So that will bring us to the difference between distance advantage and force advantage. Not all levers give a mechanical advantage. Sometimes the input force is greater than the output force. These levers make it harder to move something, but the input movement will be greater than the output movement will be greater than the input movement. If a lever makes it harder to lift heavy weights, the input force is greater than the output force. You have to exert more force on your effort, and the mechanical advantage will be less than 1. You don't get mechanical advantage there, but you get distance advantage. If, for example, the input force is 3 and the output force is 1, the mechanical advantage is output force divided by input force equals a third. In other words, a third. Okay, the mechanical advantage is a third. Okay, so you are not getting a mechanical advantage there. In the example, in the previous slide, the output force is only a third as big as the input force because the input force was 3 centimeters. And the input force, that was the input force, it was 3. And the output force is 1, so that's a third of 3. The output arm will move 3 times further than the input arm. In other words, this lever gives a distance advantage of 3. When a mechanical system changes a smaller input distance into a larger output distance, the system gives a distance advantage. Okay, if mechanical advantage is greater than 1, then a small input force over a big distance at one end can move a bigger output force over a shorter distance at the other end. A bottle opener, scissors, hammer, and pliers are examples of this. Because remember the bottle opener, let's go back to the bottle opener. We said the arm, this arm is what gives this an advantage. Okay, it makes it easier for us to remove the cap. It is the length of this arm. Okay. So I want you to see the difference between a distance advantage and mechanical advantage. Let us look at a distance advantage of 3. On a lever, the distances now the effort and the load have changed positions. Can you see that? In the other lever, we had our effort. We had our effort on the longer part of the arm, of the lever. Okay, now we have our effort on the shorter part of the lever. Let's see. Let us see. On a lever, the distances moved by the input arm and the output arm are directly related to their distances away from the fulcrum. Okay? Now, it is the effort that is closer to the fulcrum. In the other lever, it was the load that was closer to the fulcrum. If the distances from the fulcrum are equal, the distances moved, be equal, like the seesaw. The seesaw has a fulcrum right in the middle of the lever, but not all levers are like that, okay? If the fulcrum is closer to the input force, the distance moved by the input arm will be smaller. If the fulcrum is closer to the output force, the distance moved by the output arm will be smaller. Okay, now you understand why the 1 centimeter was on the 1 centimeter distance was on the output in the other was the one which was closer to the fulcrum. Now it is the effort which is closer to the fulcrum, so the effort and the lever moves 1 centimeter because on the effort is closer to the fulcrum, so the distance will be shorter. Okay, the input distance will be shorter because the input is the one which is closer to the fulcrum. Right? Distance advantage of 3. Okay. Why do we have a distance advantage of 3 here? Because the output is further away from the fulcrum. Distance advantage of levers. If the distance between a fulcrum and the input and the output is less than the distance between the fulcrum and the input, the output force will be greater than the input force, and the lever gives a mechanical advantage. So when do we get a mechanical advantage? We get mechanical advantage if the distance between the fulcrum and the output is less than the distance between the fulcrum and the input. Okay, then that is where we'll get the mechanical advantage. If the distance between the output is greater than the distance between the fulcrum and the input, the output force will be less than the input force, and the lever gives you a distance advantage. In this case, you will not get a mechanical advantage. So we need to understand this if you want to create machines where we want mechanical advantage, like the one where the guy was lifting a very heavy block. The distance between the effort and the fulcrum becomes very important. Now, grade 8, our lesson has to end here in the interest of time. We'll continue with this. I can see it's a revision of your grade 7, and you didn't have difficulty that much. But what is important is for us now, we are not repeating grade 7 work, but we are working on it to understand the mechanical advantage of levers in grade 8. Let me love you and leave you. Have a lovely afternoon.